Introduction to Implicit Differentiation. Goal here, understand the concept of implicit differentiation. What's it all about? Well, taking derivatives of functions is what's been done up to this point. But what about derivatives of relations that can't be written in function form? A circle equation, such as x squared plus y squared equals 16, cannot be represented as an f of x function. If you tried to do that, it's not going to work. You get two answers for y for every one x you plug in for most of the x's in that particular -4 to 4 interval. So can't do it. And if you graph it, you see it fails vertical line test. So you can't represent a circle equation as a function. That's why they don't call it a circle function. But there are tangent lines to the circle, and those tangent lines have slopes. There's a rate of change happening at that particular point, represented by this tangent line, the slope of the tangent line, more importantly. That means there's a derivative. That's the concept. Slope of the tangent line is the derivative value. So how can we get to that in a relation? So how do we find the slope of a tangent line to the graph of relation? Or in other words, how do we find the derivative of a relation? The approach requires thinking about this particular example, x squared plus y squared equals 16, as though it defines y as an implicit function of x. And in general, any relation that has x's and y's in as the two variables that can't be solved for y to get an f of x, which is an explicitly defined function. It tells you, when you have f of x on one side of the equal sign, you got the function rule on the other. That function rule that explicitly tells you how to get the y when you plug in an x. But in a relation where maybe you can't solve for the y even, and sometimes algebraically you can't do that in certain relations, you still have an implicitly given relationship between the y and the x. You plug in an x, and even if you have to go through trial and error, you could eventually get to a point where you found a y that would make the equation true, that relation equation true. So even though it's not explicitly telling you how to get there, there is this implicit relationship there. So you kind of think of it as an implicit function of x. And in fact, you have to consider that y itself is some sort of unknown function of x. The y variable is just kind of hiding some function of x away from you, so you can't really tell exactly what it is. So how does that work then? How does this process of thinking about it in that way work with the example relation x squared plus y squared equals 16? Well, to find the derivative of this example relation, and this is how you write it, you put the whole relation in parentheses here, and I'll let people know, hey, we're taking the derivative of this whole relation. You're going to treat the x's as normal. You're trying to find dy dx. X is the respective variable. It's what you're driving with respect to. So you just treat x's as normal. And then you're going to think of y as being the inner function of a composite. So there's some outer function whose inner function y is an unknown function of x. And by doing this little kind of mind twist, we're going to be able to use the chain rule to help get a dy dx introduced into the mix that we can solve for and find the derivative, which will give us the slope of the tangent line. We'll find this dy dx slope of the tangent line. So let's go ahead and go through this process then in this example. So you start out, you just say, okay, d dx of the relation, just writing this thing down again so we have a good starting point. And then we're going to treat the x's as normal. So x squared, derivative of that, power rule, 2x. And then we get to that y squared, so we're going to have plus something. So you think of y as being like the inner function. So the outer function is something squared. And with the chain rule, you do the derivative of the outer function. So just 2 times the inner function left alone, 2 times y. and then you multiply by the derivative of that inner function. Well, I don't know what y is defined as in terms of x, but I know if I were to take the derivative, I could represent it as dy dx. And every time you're doing a problem like this, where you're finding the derivative implicitly, and there's x's and y's, you always just tack on a dy dx every time you've derived a y, because you're essentially using the chain rule there. You don't know what y is in terms of x, but you know you've got to derive that inner function y with respect to x. So you'll always introduce a dy dx. And the beauty of that, and on the right side we'll have this 0 here, sorry. So the beauty of that, having that dy dx present every time you do the derivative of a relation in this way, you can solve for the dy dx. Even if there's multiple ones, you might have to group them together, factor out the common one, do some algebra, but you can always solve for the dy dx. And the first step here, just subtract the 2x from both sides. Then we can divide by the 2y on both sides. And then just canceling out the 2's, you get negative x over y. So what that tells me then is the slope of the tangent point, or tangent line, sorry, at any point on the circle x squared plus y squared equals 16 is just negative x over y. So for example, one point on the circle is 2, 2 root 3. Thus the slope of the tangent line at that point is negative 2 over 2 root 3, the negative x over y. Oops, I want to write that as an x. And you get negative 1 over the square root of 3 is the slope at that point. And just to take it further so we can illustrate that this actually does work out, the equation of the tangent line to this circle, x squared plus y squared equals 16, at the point 2 root 3, using the point slope form, would become y minus 2 root 3 equals negative 1 over root 3 times this quantity x minus 2. And if we go over and just look at a graph here real quick, see I got the x squared plus y squared equals 16 circle at this point right there. Let's see if I can get that honed in on the 2. 2, and then 2 root 3 would be the 3.464. You can see that green tangent line, which is the equation that I got by using that implicit differentiation to find dy dx. And that's a pretty nice looking tangent line there using that process. So if I were to put another point on the circle, I could get another tangent line equation, and I'd be able to find the slope at that point using negative x over y for this particular relation. So it always works out for you in that way. So while this is only one example of implicit differentiation, it does illustrate the general process for implicitly deriving any relation. So that is, to find dy dx, you're going to derive the x's as normal. And then you're going to derive y and multiply those results by the dy dx, because again, you're thinking of the y as being like this inner function in a composite using the chain rule. That's why you always multiply by the derivative of the inner, the dy dx. Then, after doing the derivative step, you just solve for dy dx. Use some algebra. Okay, so that is the introduction to implicit differentiation. Hope that set you up well, and thank you for watching.